All right, Chapter 5. How do we standardize an analytical method? Which, seems kind of aloof and hard to take a perspective on, but essentially, how do we create a method that actually is based on a standard? Okay, the ins and outs. And I think most of this will be intuitive, especially in the beginning. So we talked about this equation before, where the signal total is related to the proportionality constant times the moles of analyte, for example, plus we have also whatever signal comes from our reagent or our matrix. Again, the matrix is everything in the sample that is not the analyte. Okay? We're going to call this proportionality constant our sensitivity, or we could call it the sensitivity constant, because it's essentially telling us how much signal we get for every given amount of the concentration or moles of analyte in our sample. Okay? So that's what we want to do. We want to determine the value of our sensitivity and the contribution of our reagent, and make sure that they're taken into account in any experiment that we run. So we have what are called primary and secondary standards, and we talked about this a little bit before, but a primary standard is a reagent that we can use to create a standard that will be very stable over a desired lifetime. And if something is considered a primary standard, that lifetime is generally months. Okay? It's not necessarily needed to give a specific timeline for a primary standard, to call it a primary standard. But you want to be sure that you recognize, if you're working with a secondary standard, this is something that you make it up, and you need you make the solution, and you need a primary standard to kind of verify the concentration of that solution. So it's not analytically reliable to just create that solution and say, I know this is the concentration because I created it. Whereas a primary standard, that's the goal, or that's what a primary standard is. You know the concentration simply by the balances telling you how much you put in, and your glassware, analytical volumetric glassware that you use to make the solution. Other reagents you have to be careful about whether or not they can be considered primary or secondary standards at all. All right? And then when you prepare a standard solution, after you prepare that standard solution, you're also going to perform what are generally called serial dilutions, where you create the highest concentration of a desired standard, and then you make dilutions of it. You make dilutions of your sample. And you have to make those dilutions carefully, but then in the end you get, you have a variety of, so here's a nice picture over here in this chapter. Let's see, where are we at? We went too far. A nice picture of serial dilutions that were made from the highest concentration. All right? And the serial dilutions will be whatever dilution you want to make each time. Sometimes it can be half as much. Here, clearly, it's not half as much. It's just diluting by 15% about, right? Okay, very good. So, let's take a look at how we calibrate our signal. When we calibrate our signal, essentially what we're trying to do is get how much total signal is from the our analyte. If we have a standard, right, we want to know how much of the total signal is from our analyte, as opposed to the material in the matrix. Okay? So an example of creating a standard, we use a primary standard, potassium dichromate, in 0.005 molar sulfuric acid. And from some previous work somewhere, or just because we did it once and we look at it a second time, we should know what the concentration should be using a primary standard. And we get an absorbance of 0.640 plus or minus 0.01 at 350 nanometers. And that tells us that a spectrometer signal is calibrated properly. Okay, so there's a little example for us. Okay, so to determine the sensitivity, right, to solve for our coefficient here, our sensitivity coefficient, there's a couple things we can do. One, we can just run a standard, get a value, and then compare our unknown, or our analyte, to that standard for the sample, right? And find out what the concentration of our unknown, our analyte is, right? However, that's called a single point standardization, and it's the least desirable method for comparing our sample to a standard because for a couple of reasons. One, well, both of them are basically the same. The sensitivity associated with relying on a single standard is a problem, right? Because if you made any mistake in that single standard, it will be propagated. All right? And also, you're assuming that this relationship is linear for whatever your signal is compared to your concentration at all points. But that assumption is not always true. All right? If the actual relationship changes over time, then you can see how your predicted concentration from the sample signal will be different than the actual. So we want to have a multiple point standardization, which we call a calibration curve, which we've talked about already and which you are familiar with from Chem 106, but just in case, we'll mention it again. Essentially, a calibration curve gives us a relationship between our signal, whatever our signal is here, and our sample's concentration of our sample, whatever it is, and we have run multiple values here, anytime you can include a blank. I mean, you know, you're always blanking your instrument, so you theoretically always should have a 0. But then from this signal versus concentration curve, or this calibration curve, you get a relationship. Now, there are reasons why sometimes you would expect to have a linear relationship, Beer's law, for example, but there's reasons that you might not expect to have a linear relationship. And finding this relationship is sometimes part of the challenge, but generally we want to find a linear range where we can use a nice y equals mx plus b relationship between our signal and our standard concentration. All right? And this is essentially termed external standards. We're using external standards when we run this type of analysis. Again, you can use a single external standard, but that's a single point analysis. And here's some samples that you can go through and kind of use as an example. But when you have your multiple external standards and you create a calibration curve, then you get a y equals mx plus b. Hopefully you can see the y equals mx plus b. Now notice that in this equation here, y, signal from the response, that's on our y-axis, equals m, the concentration of our unknown, or our standard, whatever it is, right? M, x, right? This is the unknown. Sorry. Y equals m. This is m. This is the slope, times x, the concentration of the unknown, plus b. Oh, no, sorry. M. This is the slope here. And then x is our concentration of standard. It's on the x-axis, right? Or the concentration of our whatever we're after. And then our b value. Now, this is the y-intercept, right? And now we expected this to be 0 if we blanked everything perfectly. And if we don't get 0, then that's kind of an indication of a little bit of the variance or the error that's in our method. All right, so this is a good one to walk through. It's not very difficult, but you can compare that one. And here's another one that you can practice on if you want to. These are the kind of questions that we did in 105. So if you didn't have 105 with us or you can't remember, look through those there. An external standardization allows us to analyze a series of samples using a single calibration curve. However, we have to make sure that our matrix doesn't influence the signal at the various concentrations of our standards. All right, so it's possible that the sample's matrix could be different than the matrix that you use to create the standard solution. And for this, we would reason we would want to be sure that we match our matrices, which essentially means that if your sample is in ocean water, then you want your standards to be made up in ocean water, right? Or if your sample is in, or if your standards are in a solution of a given pH, then you also want your samples to be at that same pH, right? Okay, another way is what we call standard addition. Methods of standard addition are simply where you add a standard to your sample. All right, so you have a sample, it has some unknown in it, but then you add a known amount of your unknown. So your analyte, right? You add a known amount of your analyte. And the reason you do this is because the signal that you are expecting to see from that analyte that you added should be known, right? You should know how much signal you should see. And that amount of analyte that you added is also in the same matrix. So if the matrix influences your sample, then it will influence your added amount of analyte as well. Okay, this is called spiking your sample. Spiking your sample means that you have a sample which has an analyte in it, and you're trying to find out how much analyte there is. And you've tried different methods for determining the analyte, and it's not quite working. And so you spike it you put in a known amount of analyte. And then you have a blank with no analyte that you spike with your same amount of analyte, and you compare the resulting signals. So let's see if we can talk through an example where we spike some of our material with some of our unknown solution with a known amount of, in this case, lead ion. Okay, so we have a sample of blood, and we're looking for lead ion in it. And the signal of the sample is 0.193 when 1 milliliter sample is diluted to 5 milliliters. Now we have a second 1 milliliter sample of blood, and it's spiked with 1 milliliter of a known concentration of lead, and that's our external standard, and diluted to 5 milliliters, yielding a spike, a signal from our spiked sample of 0.419. So we want to know what the concentration of lead was in the original sample of blood. So this is the same sample of blood, right? One has our lead in it, one has our lead from the blood, and one has our lead from the blood plus the lead that we added from an external standard. So we began by looking at these equations, 539, let's see, where were we at there? Okay, so here's our 539 right here. And we're going to put our values into there. So the signal from the sample, 0.193, the signal from the spike, 0.419, the concentration of A, and that is 1 divided by 5, the concentration of A here, 1 divided by 5, plus the concentration of the standard, that much, the volume of the standard, 1 times 10 to the minus 3 milliliters, divided by 5 milliliters. So here, it looks like there's a little issue with this problem because it's saying a second 1 milliliter sample of blood is spiked with 1 milliliter of this stuff here and then diluted to 5. So the final volume is 5. And the standards volume here, they're saying is 1 times 10 to the minus 3 milliliters, which is 1 microliter, all right? Which makes sense because you wouldn't want to put a whole milliliter of your spike in. So it looks like this ml should have been a micro sign there. So either way, you just follow what the equation here says, which is the volume of your standard. And again, the volume of the standard has to be a small amount compared to the volume of your sample to start off with, the volume of your spike, right? So it doesn't make sense to do 1 milliliter. So they must have been thinking to do it in 1 microliter. So from this here, we have an equation in which we have the concentration of A twice here, right? We collect those terms and then solve for the concentration of A, and we see that its concentration was 1.33 parts per billion. All right, so this is our equation that we'll use when we're introducing a spike. All right, so it's also possible to add a standard addition directly to a sample, measuring the signal both before and after the spike. In this case, the final volume after the standard is the volume initial plus the volume of standard. Equation 5.37, 5.38, right? And 5.39 become this here, where you have your spike equaling, the signal from the spike equaling the analyte signal, this analyte sensitivity, right? Times the concentration of A, volume initial over volume initial plus the standard, plus the concentration of the standard, volume standard over the volume initial, plus the volume of the standard. So let's see if we can answer this question here. We're using the same type of setup. We're analyzing lead in blood. We got a sample of 0.712 for a 5 milliliter sample of blood. After spiking the blood with a sample of 5 milliliters, and this is probably 5 microliters, yeah, see down there, 5 microliters of 1560 parts per billion lead, an external standard, a signal spike of, the spike signal of 1.546 is measured. And we want to know what's the concentration of lead in the original sample of blood. Okay, so before we take a peek, should we try it together? Okay. All right. Whoops. Let's move that up here. Okay. There we go. Okay, so what do we know?
We know that the signal sample was 0.712.
All right, so we got a signal sample. Signal to sample, 0.712.
And then you got a signal spike of 1.546.
Very good.
And you know the volume of the sample was 5 mils. The volume of the second sample was 5 mils plus the 5 microliters.
Very good. 5 microliters. All right, and so we were trying to solve the concentration of the standard. All right, so let's look at our ratio here. S sample, 0.712, over the concentration of the analyte. That's what we don't know, right?
S spike is 1.546.
Very good. 1.546 is our S spike right here, right? And then we, oops. Then we need our concentration of the sample. That's also still concentration of our analyte, unknown. Volume initial.
The volume initial is 5 mils.
Very good. 5 over 5 times 5 plus what?
The standard. Did we add standard to this one?
Let's see. Did we add any standard to this one here? Whoops. No, in this one here, we didn't add standard, right? We're just adding the standard to the spike. Okay, so we can just leave it 5 over 5 there. And then what?
The concentration of the standard.
Very good. Plus the concentration of the standard. What was the standard?
19, what was it? 1560.
1560 times
Volume of the standard was 0.005.
0.005, that's what?
That's in milliliters, right? 5 microliters.
Very good. And then the volume initial was 5, and then we put our 0.005 down there. All right, so should we work that out?
Okay.
I'm going to push pause as I work that out in the calculator. Why don't you try it as well and see if you get it? All right, so if we got our calculations done, you can look through those and make sure that they match yours, and we get 1.33 parts per billion. All right, excellent. Now, if we wanted to use multiple standard additions, we can adapt a single point standard addition into multiple standard additions by preparing a series of samples that contain increasing amounts of external standard. And what that would do is it would shift our curve, right? Our plot, which typically starts at 0 and increases, is going to be shifted up, all right?
Why would you do that?
Well, because you want to know how the 0 responds in there. And so basically you have your samples, all sorts of all these are samples, but they're all spiked. And so now instead of relying on one spike sample, you have a series of spiked samples. So all of your backgrounds are the same. And what that does is it does something interesting where there's a straight line, which is a curve, and it's easy to show that the x-intercept is equivalent to a negative value of the concentration of your analyte, all right, divided times the volume of your initial volume, divided by the concentration of the standard, all right? So let's look at this equation here in 3.38, all right? This one here, where we looked at the spike concentration, right, this relationship, which boiled down to this for us, right? Where are we at now? Down here, okay. If we look at that and show the equations, so that the equations in 530.36a for the slope, the y-intercept, and the x-intercept are correct. So we're basically deriving this relationship, showing that the x-intercept is indeed the concentration of our analyte times the volume of our solution divided by the concentration of the standard. So let's try and see what kind of experiment, or let's perform an experiment using multiple standard additions and see what this does for us. All right, we used multiple point standard additions based on this equation, and the original blood sample had a volume of 1 milliliter, and the standards used for spiking the sample has a concentration of 1560 parts per billion. All samples were diluted to 5 milliliters before measuring the signal, and a calibration of curve was found with this as our equation. Y, signal from our spiked samples, or just signal, equals m is our slope there, times x with mx plus b value, a y-intercept value of 0.266. And then we want to know what the concentration of lead ion was in the original sample. Okay, to do this, all we need to remember, right here, this is our resulting slope of our line. Our y-intercept is not close to 0 anymore, right? And if we can find out where this line crosses the x value here, then we should be able to relate that cross to that intercept to the concentration of the analyte. Okay, so we set our signal to 0, and 0 minus our 0.266. We move it over to the other side, so we're going to solve for the volume of our standard. So minus 0.266, and then divide by our 312, right? So solving, putting a 0 in here, getting our negative 0.266 when this moves over to the other side, divided by 312 gives us a value of 8.526 times 10 to the minus 4. And now that volume of our standard is equal to the concentration of the analyte times the volume original of our samples, which was 5 milliliters, and divided by the concentration of the standard. Okay? Oh, the volume initial wasn't, that was the dilution volume of 5. So our initial volume was 1 milliliter. Okay, so solving for our CA here, right? Taking our negative 8.526 times 10 to the minus 4th, multiplying it by 1560 equals, and then dividing by 1. So that's a negative 1.33, but the definition of it is a negative value. So that gives us, again, our 1.33 parts per billion. So what did we do there? We made a plot like this, essentially, and we were solving for what the value is over here. All right, so what the value is, the x-axis intercept over there, and then changing the sign to a positive value tells us our concentration of our analyte. All right, let's see if we can do it together without help. All right, so we have a standard addition curve, calibration curve. All right, for manganese, each solution contains 25 milliliters of the original sample and either 0, 1, 2, 3, 4, or 5 milliliters of 100.6 milligram per liter, that's parts per million, external standard of manganese. All standard addition sample were diluted to the same volume, all right, with water before reading the absorbance. So the equation for the calibration curve is the same as before, 5.36. Where is it at here? The equation for the calibration curve in figure 5.36 is this. So here we have our y equals mx plus b for our equation. And again, this time our m and x are right here and the b's over there. Good. So if we set this equal to, so we want to know the concentration of the manganese in the sample. All right. So I'm going to look at a scenario where my S standard, my signal from my sample is at 0. Does that make sense?
Well, I think so, but I'm not quite sure why.
Well, let's draw a little picture for ourselves here. So we have a calibration curve, and this is the equation for that calibration curve. But it's not just a typical calibration curve, it's a calibration curve of standard additions, right? So the calibration curve for this standard addition looks like this, where we have a sample which has some amount in it, but then we've added standards to all of these. Standard amounts, or amounts of a different standard. And it said 1, 2, 3, 4, and 5. But all of that is kind of encompassed in this one equation, so we don't have to take into account those values. Because we already showed that the intercept over here, right, is related to this right here, is related to the concentration of the analyte times the initial volume of our unknown, of our solutions, our unknown solutions, divided by the concentration of the standard, a negative value. All right, that's what this intercept equals. Then what we can do is we can set this value equal to 0, basically, so this is our y equals mx plus b, and we look for where y value equals 0, which will be our x-intercept. So we set that one equal to 0. So if we do that, we get 0 equaling 0.0854 V standard plus 0.1478. So we're going to solve for the volume of our standard here by subtracting our negative 0.147, or subtracting our 0.1478. Okay, and then we can divide by 0.0854. All right, so we got a value of negative 1.731. So if this is our x-intercept, we can set that equal to this here, negative 1.731. We have our volume initial, which was 25. All right, so let's solve this problem here now. 25. We want to know what our concentration of our unknown is, of our analyte. And then the concentration of the standard, we're told, was what? Where is it at here? Concentration of the standard was 100.6 parts per million. So 100.6, sorry, 100.6, there we go, equals negative 1.731. So we can divide both sides by negative 1 to start off with, or just take our negative 0.1731 and multiply it by our 106, or 100.6. Okay, so that is going to equal to 25 times our concentration of our analyte. So divide by 25. Again, get rid of that negative sign because this is a negative sign over here. So we got 6.96 units are, that's parts per million. So milligrams per liter are parts per million. All right, so again, just a quick review. We solved for the x-intercept and then set that x-intercept equal to what this is, which is the concentration of our analyte times the volume initial divided by the concentration of the standard. Okay, good. Now, because of the nature of this problem, or these standard addition problems, or experiments, you have to take lots of sample and add known to each one, right? And that makes it kind of a destructive experiment. Not that it wasn't destructive before, but it's also kind of dependent on every sample. So instead of making one standard curve that you could use lots of samples on, every time you want to analyze a sample, you have to make a new standard curve. Okay? And that's a serious drawback to this sort of a method. But it can be very helpful and accurate. So it's also a good way to use standard addition to identify what we call matrix effects. So matrix effects, again, are anything in the solution that's not your analyte that changes the way that your analyte creates a signal. All right. So when you create a curve, a standard curve, from just your addition of external standard, right, to a solution hopefully that is free of your matrix, and then you compare that slope, right? That slope is the signal to a standard addition curve, and the change in that slope will give you information about your matrix effects. Okay. So in the process of preparing a sample, oftentimes the method of preparation itself, or the protocol, procedure, will result in changes in the concentration of your analyte. For example, if you have anything that's volatile, or if the matrix gradually reacts with your analyte, that could be a problem as well. Generally, more importantly, is volatile solvents, right? If you have a volatile solvent and your concentration, therefore, is always changing as your solvent evaporates, that's a problem, okay? So another way that we can address this problem is use what we call, an internal standard like we talked about, but an internal standard that's a different chemical, completely different analyte. And we still have to have a method to detect it. But if we know its concentration, and its concentration is the same throughout, then when we run the assay and we get a response for that internal standard, we know that response, we'll know whether or not that response has changed for whatever reason. Okay? And there's a handful of types of techniques where this becomes useful. All right, we're not going to go through any practice problems for this set here.